Another important point about spatial data is to understand spatial correlation. And to begin, I would like to quote Tobler's phrase from 1970 that states, geographically, everything is related to everything, but near objects are more related to each other than distant objects. So, what does this mean? For example, this is a map of the American population in the United States. And if I'm in a point where the um, density is low, it's more probable that my neighbor lives in a lower density also. So if I'm in a point that there's higher density, then probably my neighbor is going to be in a place with a higher density. So the closer I am, the more related I am. And in order to demonstrate this, if the data was random, then we would have a map like this one. These maps aren't the same, or the patterns aren't the same. So this is not random. There's a correlation, a spatial correlation. And the same thing applies for the map for elevation, for the altitude. So this is the map for the altitude, but if the map was random, it would look like this. And it is not. So this means that there's a spatial dependency. And this applies for the vectorial data, for polygons, and also for the data that's raster data, like the one with the pixels. So for every spatial data, it doesn't matter how it's being represented. Normally, this spatial correlation exists. And this spatial correlation is positive, and this means that it's what's closer, it's more similar. So there's a positive correlation to the neighbors. But it's also possible that this correlation is negative. So for example, if I'm in a black square, most likely when I change, I'm going to go into a white square. So this would be a negative correlation. So my neighbors have a different value to my value. And finally, this is an example where there are no correlations. They are independent because there are points. There appears to be that there are positive, negative points. So there's no clear correlation. So these are independent. It's important to take this into account because a lot of the statistics that are used, one of the suppositions is that everything is independent. But in practice, when spatial data is used, many times it's not correlated. So you have to choose the proper methods where you can work with correlated or not non-correlated data. Another interesting concept for quantifying that level of correlation, spatial correlation, is how the neighbors can be seen. These are two simple examples. You can have as a neighbor, this would be the rook type, where part of the border is shared. But you can also have the queen criterion, where a vortex is being shared, and it's going to be considered as a neighbor, which is what's happening here. So the ones that are in yellow in this case are all neighbors of one of the squares that are white, and due to this queen criterion. This is important because in order to quantify the correlations space, this is the assessment that's done within the value of the interest and the value of the neighbors. In order to determine the neighbors, we can see this example, which is like the rook, but you can also use the distance criterion. Let's say that the center to the other center is at a distance less than 100, so I'm going to consider it as a neighbor, otherwise no, not. And you can see that this one that's apart over here has no neighbors because of this criterion of 100 kilometers. And the two closest ones can also be considered. The ones that had the least distance are considered as neighbors. So in this way, we would have a uniform amount of neighbors. In this case, some of them have 6, other 4. In this one, have there's 9 neighbors, and the other one has 0. In this one, they all have 2 neighbors. So there are advantages and disadvantages on how to define these criterions. Generally speaking, it depends on the problem and the answers that you want to obtain. So this is a part that requires a little bit more knowledge of what you want to use that information for. This is another example with the data that we're going to work on in the Chiapas state. So I'm using the neighborhood criteria. So the red lines are all the relations between the neighbors. And we don't have all the municipalities, but there are 140 municipalities and there are 570 links. This is a percentage and an average number of links. That would be 5. This is the distribution. There are 5 municipalities with just one neighbor or one link. And the average here would be 4 or 5. They have the largest numbers. And finally, 3 municipalities have 10 neighbors, which are the ones that are concentrated in this part. Once the criterions for neighbors have been defined, what you have to do is to calculate the average of the value of interest in every neighbor. We can also have different weights or values, but for simplicity, let's just say that this would be the simple average of the values with every neighbor. And for every point, you could have the value of the variable in the point of interest and the average value for the neighbors. By doing this, you can create a dispersion plot like this one, where I have the yield data for maize in some points. This would be the yield in this point, let's say 3 tons per hectare. And this would be the average yield for our neighbors. So I establish who were the neighbors or which were the neighbors, and I have the average. Right here I have a point where the neighbors have an average of 2.7 approximately, and the value here would be approximately 2.7 also. So the spatial correlation measure is directly related to this angle, to the angle of this line that establishes the relation between the value in the point and the average value of the neighbors. So this is one of the spatial correlation measures that's most oftenly used, and it's known as the eye of Moran. So this value goes to -0, -1 to +1, and it can leave this interval, the amount of samples, if it's very small. But generally speaking, it's within this range, where 0 would be a non-existent correlation. This would be independent data, and the value of 1 would be a perfect correlation. So when the values are correlated, and a correlation of -1 would be a negative correlation, because I always have a high value close to a low value. This is an important concept to take into account because there are different indexes to use to represent the spatial correlation, but the principle is very similar to this one, where you compare the value in a point with the value of the neighbors. And this applies for pixels, for points, polygons, and all the others. Each of one have their specificities, but it's important to understand the concept. And this is the example of the result of the calculation of the I for Moran in R. So I have this data, and I use the function for calculating the I for Moran, and right here is like 0.54. This is a very strong correlation, a positive correlation, and that demonstrates that the data is not random. And this is the value of the p-value. So it's almost impossible for this result to be due to luck or randomness. So we can conclude that this information has a spatial correlation and that the value of the correlation is 0.54.